Dear students, we are in the unit complex integration. So you know now the first heading in complex integration is Cauchy's integral theorem, then Cauchy's integral formula, then formula of derivatives, and then some problems, right? We did some problems. And the second heading is Taylor series and Lorentz series. Now this is the third heading, classification of singularities. So we have already studied about singular point in the unit analytic function. I told you the definition in as a last topic of third unit. Last topic. The function f of z ceases to be analytic, right? So definitely there I defined about singular point. And anyhow, let us define once again the definition of singular point. A point f of z, a point at which f of z is not analytic, is said to be singular point. See, for example, f of z equal to 1 by z minus 1 whole square. This function is analytic, but when z is 1, this function will not exist. Hence, the function is analytic except at the point z equal to 1. So, a point at which f of z is not analytic is called a singular point or singularity, okay, of f of z. Have you understood now what is a singular point? A point at which the function is not analytic is called singular point. There are some types of singularities, classification of singularities, right? So you know definition of singular point. Now we have four types of singularities: isolated singularity, pole, essential singularity, and removable singularity. Let us see one by one the definition. Isolated singularity. Once you find the point is singular point, you have to test whether the singular point is isolated singular point or pole or removable singularity or essential singularity. So you have to test what kind of singular point it is. Okay. For isolated singular point, listen here. If you see if z equal to, here z equal to 1 is a singular point, right? Function is not analytic when z is 1. This z equal to 1 is isolated. Reason is, so you draw neighborhood of z equal to 1. In the neighborhood of z equal to 1, you cannot find any point where the function is not analytic. Such point is an isolated singular point. Listen here. At z equal to 1, you draw, you see some neighborhood. Some neighborhood of at z equal to 1. At those neighborhoods, listen here. Each and every point of such neighborhood, you cannot find the singular point. Okay, the point z equal to a is called an isolated singularity of f of z if there is no other singularity in its neighborhood. So z equal to 1 is a singular point. The neighborhood of z equal to 1, at neighborhood of z equal to 1, you cannot find any point where the function is not analytic. Okay, such a singularity is said to be isolated singularity. You can see another example: z cube into z square plus 1. This function is analytic except when z is 0 and when z is. So how will we find the singular point here? Equate the denominator to 0. Equate the denominator to 0 so that 1 by 0 we will get. Okay. Equate the denominator to 0. You can get the singular point. Equate the denominator to 0. Z cube into z square plus 1 equal to 0. Z cube equal to 0. Z square plus 1 is equal to 0. Z square is equal to minus 1. Then z equal to plus or minus I. Right? So z equal to 0 will make the function which will not be analytic. Z equal to I or minus I will also make the function not to be analytic, right? So those points are singular points definitely, and they are isolated singularity because at those neighborhoods we cannot find any point where the function is not analytic. Okay, you find neighborhood of z equal to 0, you cannot find any point of neighborhood of z equal to 0, the function is not analytic. Hence it is an isolated singularity. Similarly, so how will we find singular point? The denominator should become 0 so that the function is not analytic. If to make denominator 0, equate the denominator to 0. Z minus 1 whole square is equal to 0. z minus 1 is equal to 0, z equal to 1. Similarly, equate the denominator to 0. You will get points z equal to 0, z equal to I square is minus 1 plus 1, 0. Minus I whole square is I square, minus 1 plus 1, 0. So equate the denominator to 0, you will find singular points. And you have to test whether the singular point is isolated singular point, okay? Next comes the second type of singularity is pole. What is pole? An isolated singular point A is called pole. So if once you know the point is isolated singular point, then the point is pole. Z equal to 0 is a pole. Z equal to 1 is a pole. But it is a pole of order 1. This Z equal to 1 is a pole of order 2. So a pole of order 1 is otherwise called simple pole. Simple pole. Okay. So isolated singular point is called a pole. Or even simply we can say singular points are poles. Singular points are poles. Okay. This is second type of singularity. So you know what is singular point. A point at which function is not analytic is called singular point. You know isolated singularity. If the point is a singular point, then it is an isolated singular point if we find no point in the neighborhood of the z equal to 1, here z equal to 1 is a singular point. Okay. Isolated singular point is pole, or simply singular points are poles. Okay. Singular points are poles. So pole of order 1, pole of order 2. Pole of order 1 is otherwise called the simple pole. Simple pole. Okay. Next, third one, essential singularity. So the essentials, to find essential singularity, listen here. In Lorentz series, if there are infinite number of terms, let us see through example this essential singularity. See, this is an example. We know the expansion of e power x, which is 1 plus x by 1 factorial plus x square by 2 factorial plus x, etc. Right? This z equal to 0 is an essential singularity because it is Lorentz series. You know in Lorentz series we have principal part and analytic part. That is negative powers of z minus a and positive powers of z minus a. Here you can see we have only negative powers of z minus 0. Z power minus 1, z power minus 2. There are no positive terms here. So we have z minus a, actually a is 0. Z minus 0 is z. Z minus 0 whole square is z square. So we have only negative powers of z minus a and no positive powers. So we have to find whether the point is essential singularity or not. We have to get Lorentz series. And if you look at the series, you can find only not only infinite number of negative powers. We have infinite number of negative powers of z minus a. Then such point is essential singularity. Let us read definition now. Definition. See, in Lorentz series of f of z, if there are infinite number of terms containing negative powers of z minus a, then z equal to a is an essential singular point. Okay, essential singularity or essential singular point. This is an example. We have here infinite number of negative powers of z minus 0. Hence z equal to 0 is an essential singularity. This is the fourth kind of singularity, last kind of singularity. Removable singularity. What is removable singularity? See, we have two definitions for removable singularity. According to the situation, we use definition. Okay. So you should know both definitions. Using Lorentz series, you can get removable singularity. See, we know expansion of sin z. Now you can see, after multiplying z, see sin z by z. Example, expansion of sin z. Multiply this denominator z. Take limit. Listen here we identified already. When you equate denominator to 0, you will get singular point. So it's very clear, z equal to 0 is a singular point. Z equal to 0. So limit f of z approaches 0, which is 1. Okay. So z equal to 0 is a removable singularity. That is what we have in Lorentz series. Z equal to A does not contain principal part. You can see this is Lorentz series. There are no negative powers of Z minus A here. Only positive powers. There are no negative powers here. We have only positive powers. You can see they are different, right? In essential singularity, we will have infinite number of negative powers of Z minus A. In removable singularity, we will have no negative powers of Z minus A. No negative powers of Z minus A. They are different. So you can easily classify whether the point is removable or essential. Here we have infinite number of negative powers of Z. Here we have only positive powers of Z, no such number. So when see, Lorentz series of f of Z about Z equal to A does not contain the principal part. That is negative powers of Z minus A. Then this Z equal to A is called removable singular point. What is another definition? Another definition is easy. Directly we can, see, in case if the function is not sin Z, some other function where we cannot write expansion or denominator is different, where expansion cannot help. Denominator is different. Expansion cannot help. Here you can see Z by Z is 1. In case Z plus 1, how will you do? Where expansion cannot help. In such case, we use this definition. Limit Z tend to A f of Z. If limit of the function exists finitely, then the point is called removable singular point. Okay. So what is removable singular point? There are 4 types of singularities. What is singular point? A point at which function is not analytic is called singular point. How will we identify singular point for the given function? Equate the denominator to 0, you will get points, they are singular points. There are 4 types of singularities: isolated, essential, removable and pole. What is isolated singular point? If you find neighborhood of the singular point, you cannot find any other point which is singular other than the point obtained. Such point is isolated singular point. Okay. Now you know meaning isolated, right? தனிமைப்படுத்தப்பட்ட, தனிமையான. You cannot find any nearby points which are singular, right? And what is pole? Second singular point, pole. What is pole? Pole is an isolated singular point. Isolated singular point is pole, or simply singular point is pole. So we may write the order of pole. Pole of order 1, 2, etc. Right? Pole of order 1 is called a simple pole. And what is the essential singularity? Let us see difference of essential singularity and removable singularity. Essential singularity and removable singularity, we write Lorentz series for the function. From Lorentz series, we write answer. If Lorentz series has infinite number of negative powers of Z minus A, then Z equal to A is an essential singularity. If Lorentz series has no negative powers of Z minus A, then Z equal to A is a removable singularity. Okay, that is the difference. And we have another definition also. We shall discuss in problems. Okay, we shall discuss these things in problems. See, there are remarks. Okay, and remarks and problems we shall see next in the next video. And definitely you will feel easy. It is easy heading. Okay, easy heading. Though the theory is, if you think it is confusing, but when you see problem, after seeing problem, if you go to theory, definitely theory will be easy. Okay, after seeing problem, you go through theory, so the theory will be easy. Okay, let us see the problems. So before seeing problem, let us see what is meromorphic function. See, meromorphic function, this is the example of meromorphic function. So it has only 2 poles, Z equal to 0 and Z equal to 1. A function f of Z which is analytic everywhere except at finite number of poles is called meromorphic function. So this function is analytic everywhere except at Z equal to 0 and Z equal to 1. Hence it is meromorphic function. So a function which is analytic everywhere except at finite number of poles is called meromorphic function. And we have already seen when can we say function is analytic everywhere. The function which is analytic everywhere is called the entire function. The function which is analytic everywhere is called the entire function. See, except at infinity. E power infinity, infinity. And something, examples. Cos z, sin z. We have proved e power z, cos z, sin z are on analytic functions. We have proved it satisfies CR equations and it satisfies other conditions, sufficient conditions of analytic function. So they all are analytic everywhere. Okay. So they are called the entire function. Now comes problems. Find the nature of singularities. So function is given. Nature of singularity. There are 4 kinds of singularity. We have to test one by one the singularity. First you find singular point. Before going to the types of singularities, first equate the denominator to 0. Z cube equal to 0. So that Z equal to 0. So Z equal to 0 is the singular point. Okay. So it's very clear that Z equal to 0 is a singular point. Because at Z equal to 0, function is not analytic. After finding singular point, now let us discuss the types of singularities. And this singular point is isolated singular point because in the neighborhood of Z equal to 0, no other point is singular. And we know isolated singular point is pole. So this Z equal to 0 is a pole, but it is of order 3. Okay. So we know isolated singular point is a pole. So we have discussed the first type of singularity, second type of singularity. Now comes essential and removable. So if removable singularity comes, essential will not come. Right? If essential singularity comes, it will not come. I think so. Because in Lorentz series, when we have infinite number of negative powers of Z minus A, we talk about, what will we talk about? When we have infinite number of negative powers of Z minus A, we talk about essential singularity. If there is no negative powers of Z minus A, we talk about removable singularity. So, if that one comes, we need not discuss the other one, right? See, f of Z is 1 by Z cube. Let us split sin Z by Z cube minus Z by Z cube. We know expansion of sin Z. I have given as a remark all the expansions, okay? Sin Z has expansion Z minus Z cube by 3 factorial plus Z power 5 by 5 factorial minus etc. This plus Z by Z cube and minus Z by Z cube get cancelled. Z cube get cancelled 1 by 3 factorial with negative sign. Z cube Z power 5 get cancelled, it becomes Z square. So this is the answer and this is our Lorentz series. It is our Lorentz series and in the series there are no terms, negative powers of Z minus 0. Z minus A, actually A is 0 here. No negative powers of Z minus A. So we should talk about removable singularity. And we cannot talk about essential singularity here. Okay. So here we should check whether limit of the function exists. If limit of the function exists, it is removable singularity. Okay. So Z equal to, is when Z approaches 0, all the other terms will become 0. 0 by anything 0. Answer is minus 1 by 3 factorial. Limit of the function exists finitely. Right. Hence Z equal to 0 is a removable singular point. So once you know expansion and from series you can easily decide whether it is removable or essential. Okay. Let us see next problem. Classify the nature of singularity. Tan Z by Z. See, then equate denominator to 0. You will get singular point. Let us discuss types of singularity. Z equal to 0 is isolated singularity. It is isolated. Taniya irukku. Isolated singularity. No other neighborhood of Z equal to 0 is singular. If it is isolated singular point, then it is pole. So Z equal to 0 is a pole, but it is of order 1. And now we have to talk about removable and essential. To talk about removable and essential, let us use expansion to get Lorentz series. I have given you formula of tan Z, need not worry. I have given you in the next page the form expansions which we use in the heading, okay? Tan Z is Z plus Z cube by 3 plus Z power 5 by 5 plus etc. Multiply this 1 by Z. You can see there are no negative powers of Z minus A here. A is 0. No negative powers of Z minus A. Hence, then we need not talk about essential singularity. Just removable singularity. See whether limit of the function exists. If it exists, it is removable singularity. You can stop here. You can stop here. It is 2 mark question. You will get marks. And if you know, you can proceed. You can proceed. How to proceed? See, being tan z, we know tan pi by 2 is infinity. So the function is not analytic when we have infinity, right? When z is 0, it becomes infinity. Similarly, tan pi by 2 is infinity. Tan of minus pi by 2 is infinity. Tan 3 pi by 2, tan of minus 3 pi by 2. At all those points, function is not analytic. When function is not analytic at the points, then the points are called singular points. Points are called singular points. F of z is not analytic at these points. Hence, they are singular points which are called isolated singularities and poles. They all are isolated singularities and poles. Okay, which completes second problem. Let us see next. Find the pole and its order for f of z equal to z cube into z minus 2. Pose, simply pole and order. So we need not talk about other things. Okay, we need not talk about other things. Z equal to 0 is a pole of order 3. Z equal to 2 is a simple pole. Enough. Okay. So these two are the singular points and they are isolated singular points. Hence they are poles. That is enough. I told you that I have given you expansion, right? And these are the expansions which we use here. Okay. Next to see, identify the type of singularity. E power z square by z cube. Sorry. Oh, I do not know whether I have done second problem. Okay. E power minus 2z by z. Z equal to 0 is a singular point. Okay. It is singular point. Because when you equate denominator to 0, you identify singular point. It is isolated, no doubt. It is isolated singular point. If the point is isolated, then it is pole. Okay. So z equal to 0 is a pole. Now let us use expansion to find removable singularity, essential singularity. We know e power minus 2z expansion. E power z expansion 1 plus z by 1 factorial plus z square by 2 factorial, etc. Multiply the term. You will see like this. Like this. See, all the terms are with positive powers. And only one term is with negative power. See, when there is no negative power, we talk about. When there is no negative power, what will we say? When there is no negative power, we say removable singularity. But we have negative power here. So there is no discussion of removable singularity. When there is no negative power, even one term, there is no negative power, we talk about removable singularity. But we have negative power of z minus a, z power minus 1. Okay. So we cannot talk about removable singularity. Can we talk about essential singularity? For essential singularity, we should have infinite number of negative powers. And that is also not here. See, only one infinite power, only one negative power. If you have infinite number of negative power, we talk about essential singularity. So, in Lorentz series, principal part is 1 by z. Only one negative power. And also number of negative powers of z minus 0 is not infinite. So, we cannot talk about essential singularity and removable singularity. Both are not possible. Because for removable singularity, there should be no negative power. For essential singularity, there should be infinite number of negative power. You can see both are not here. Hence, there is no talk about essential singularity and removable singularity. Okay. I have given you homework problems. You can stop here. Okay. Need not worry. You can stop here. So, for 2 marks, it is enough. And if you know, you proceed this step. Okay. If they ask you to find pole and order, simply find pole and order. You need not find other things. Okay. And next come see singularity of e power 1 by z minus 4. If we have denominator z minus 4, we talk about pole, etc. Here the denominator is in the power of exponential. So no such thing. We cannot talk about pole here. We cannot talk about pole here. See, e to the power 1 by z minus 4. So let us take is the expansion method. Do e power z expansion. E power z formula you know, right? Expansion. Use expansion. You will see z equal to 4 is an essential singularity. You can see there are infinite number of negative powers of z minus a. So it is an essential singularity. And it is see e power z by singularity. So we equate denominator to 0. You can see plus or minus 2i. So they are singular points. They are isolated singular points. First type over. When isolated, then they are poles. Second type over. To talk about removable and essential, we usually use expansion method. But here expansion method cannot help because you look at the denominator, it is z square plus 4. If you multiply with each and every term in the expansion, you cannot guess whether it is removable or isolated, essential. So in such case what we do is, we see whether limit of the function exists. Limit of the function exists. We have identified, right? Limit of the function at z equal to 0 exists. Hence z equal to 0 is a removable singular point. Okay, it is removable singularity. And we have, this is the essential singularity. Use expansion method and you will see there are infinite number of negative powers of z minus a. So essential singularity. Okay, z equal to 0 is removable singularity, but z equal to 0 is not a singular point, right? Z equal to 0 is not a singular point. You can see z equal to 0 is not a pole actually. It is not a pole. The poles are 2i and minus 2i. The poles are 2i and minus 2i. Z equal to 0 is not a pole. It is not an isolated single. It's not a singular point. It's not a singular point. But at z equal to 0, limit exists. How will we say limit of the function exists? Limit z approaches 0, e power 0 is 1 by 4. 1 by 4. You try by expansion also, e power z. What is e power z? So that cannot help, which is very clear because denominator is z square plus 4. Okay. So please go through the problems, and if you feel any of the problems difficult, you tell me, okay? Tell me, I send you another video. Solving the problem, explaining the problem, I send you another video, okay? Thank you, ma. This heading is over. This heading is over. And next we should start residues, okay?